So we've seen how we differentiate exponentials. So let's now use that idea in a rates of change question. Probably the most common idea when it comes to exponentials is this idea of growth and decay. Radioactive decay, population decay, all this growth and things like that. They all involve the exponential function. It works on a basic assumption, and there it is there, that the growth or the decay, depending on what you're looking at, is always proportional, and I'm using the example of population there, but it's always proportional to the population that you have. I suppose if I was talking about radioactive decay, I'd say it's proportional to the mass of material that you would have. And it makes sense, I suppose, because the more population you have, then obviously the greater the growth, and unfortunately the greater the decay as well. So it kind of makes sense that it's proportional. So the rate of change of population, we're saying, will always equal to a constant times the population that we have. So that's a key formula there. Now, at this stage, to go and prove the solution to you, we'd have to know how to integrate, and we haven't done that bit yet. So we can assume the answer at this stage. So it's a simple model, and the solution to that differential equation, which is just basically a name for an equation that involves a derivative, is that. There we go. So P would end up equaling some constant times an exponential function. So e to the power of kt. T would represent time. K again is just some constant. So let's have a look at an actual HSC question. I went and found one that didn't involve integrating, so one that we could look at and see how we do. And 2015, so a few years ago now. And they're looking at the amount of caffeine in a body. So someone drinking lots of cups of coffee and things like that. So they're saying that it gets out of your system at a rate of negative 0.14 C, where C is the amount of caffeine in your body at that particular time. And they're told us that's going to be measured in milligrams and T is going to be measured in hours. So the first part is to show that it is a solution. So we don't actually need integration to solve this because we can do it in reverse. Instead of starting with the differential equation and integrate and get the answer, we can start with the answer, differentiate, and show we get the differential equation. So let's do that. There's our supposed solution. The amount of caffeine would be AE to the minus 0.14 T. And if we were to differentiate that, well, what we saw was you differentiate the power, and in this case, it's just a linear function. So differentiate minus 0.14 T, we'd get minus 0.14, and then multiply it by the exponential function. But we know that C is equal to AE to the minus 0.14 T. So I could just substitute in for that, and we've come up with the differential equation that we had to solve. So that's showing that, yes, this equation does solve the problem. So from this point on, we can assume that's the correct equation. So part 2. So in time equals 0, so initially there's 130 milligrams of caffeine in the body. We need to work out what the constant A is. All right? It really just becomes a substitution question for me. So when T equals 0, they've told us C is 130. So if we substitute that in, we get 130 equals AE. Well, if T is 0, the power becomes 0. E to the power of 0 is always 1. So A is 130. So now they want to know how much caffeine is going to be left in the body after 7 hours. So when T equals 7, again, it's a substitution question. So 130, we've worked out A is 130. E to the power of minus 0.14 times 7, which 48.7904, and the calculator goes on. I've done it to 1 decimal place there, so 48.8. So I answer the question. So it's about 48.8 milligrams of caffeine left in the body. How long? And actually, this question is quite common in science when it does come to the radioactive questions, because it's a thing they call half-life. It's the same sort of idea here. They're saying, well, how long does it take for the amount of caffeine to halve in this case? So half would be 65, So basically that's what they're asking us to find. When is C equal to 65? So let's sub that into our equation, and it's not a coincidence, surprise, surprise. Look what happens, we're solving when is the exponential equal to a half. Makes sense, we're finding the half-life. All right, well, to undo the exponential, we'd log both sides. But it needs to be the natural log because we're working with base E. So I now know minus 0.14t is log of a half. Divide by minus 0.14, that would be the exact answer. But I suppose when we're answering a question like this, that sort of exact answer doesn't really make sense. I mean, if someone said to you, how long is it going to take? You wouldn't say, oh, I think it'll take minus 1 over 0.14 log a half. Doesn't really give you a feel for how long that is. So if we go to our calculator, there we go, we get a answer 4.95105 and so on. So around about 5 hours for the amount of caffeine to halve. So that's a typical sort of 2-unit HSC question on the growth and decay. All right, so 11F, I've just picked out, oh look, I was going to say it's the odds, but look, number 8's in there. So in a way, it is odd, because it's all the odd ones, but then there's number 8, which is not odd, which makes it odd.